Hi everyone, my name is Chambar Manoj. Today I am going to present our work 360NorVic, 360-degree video traffic classification from mobile encrypted video traffic. So before moving to the presentation, I would like to give you the presentation flow. I'll start from the describing the current 360-degree video streaming platforms and what are the challenges related with that. And then I'll briefly describe some related work with the 360-degree video streaming, followed by our 360NorVic methodology. And then I'll show you the results of the 360NorVic performance, followed by the conclusion and future works. First, let's see how the current 360-degree video streaming platform works. As you can see this end, first of all, we need to capture video frames using a specific camera called omnidirectional camera, or using powerful computational platforms. We can create 3D animated VR scenes. Once we have created these video frames, those will be stored in the content servers in different quality levels to support the dash video streaming. And once the video frames are ready, they will be transmitted through the network to the client based on their request. And the client side, they will watch these videos either using a head-mounted device or using a smartphone in monoscopic or stereoscopic view. So now let's see what are the challenges related with 360-degree video streaming. To gain the same user-perceived quality, these 360-degree video frames should be 4 to 6 times larger than a normal video frame. And at a given time point, the user will see only a specific portion or a small part of the entire video frame, as you can see in the right side figure. So there will be an excess amount of data transmission, causing high bandwidth wastage, frequent rebuffering, and low bit rate of the video, and then of course the high computational cost at the end devices, which will be essentially cause a poor quality of experience. So now let's see a couple of works that are related with 360-degree video streaming. Tile-based streaming has been the most promising solution, where they divide the entire video frames into tiles, and the tiles within the user viewport will be streamed from the servers in high quality, and the remaining area will be in low quality, reducing the bandwidth consumption. And also there are a couple of works related with live streaming of 360-degree videos in controlled environments, where they measure some quality of experience parameters, how they can affect this 360-degree video delivery. However, we couldn't see any prior work on classification of 360-degree video traces and normal video traces while collecting encrypted traffic data from the network. So that has been another motivation for our work as well. So what is the importance of a prior identification of 360-degree video traces and why we need machine learning? So having identified 360-degree video traces at the beginning, we can manage and allocate resources efficiently for 360-degree video flows, enhancing the quality of experience. And also we can maintain traffic shaping and policings. And with the long-term analysis, we can manage to have a proper long-term capacity planning. For example, we can come up with efficient caching and compression strategies. So in our work, why we have used machine learning? Because we know that today almost all the network traffic is end-to-end encrypted. So traditional approaches such as deep packet inspection is less usable in terms of network traffic analysis. And also, under varying network conditions, we saw that both video types, 360 and normal, showed very similar properties that we need to analyze subtle feature differences in order to make a proper classification. And also we have seen many prior works with decent classification performance in network traffic analysis domain. So these were the motivation facts for using the machine learning in 360NorVic. So here onwards, I will describe our methodology that we have used in 360NorVic, starting from the dataset. So we have streamed 360 and normal video traces from both YouTube and Facebook. As you can see in the table, for each video category, YouTube 360 and normal, Facebook 360 and Facebook normal, we had 50 unique videos which claim more than 600 traces in total by repeatedly streaming those unique videos. And we have collected both packet and flow level data from 3 different vantage points of the network. First, the LAN, local area network, that we collected the packet level data. Here onwards, we will denote it as a DS packet. And using those packet level data, we emulate the flow level data that we can collect from enterprise network, which we denote as DS flow. And finally, we collected flow level data from large operation network through their deployed middle boxes that we denote as DSMNO. And we stream the videos under different streaming conditions. For example, time, and also different video genres. And also we used bandwidth under not control condition. Next step of 360NorVic methodology is data preprocessing. So in this step, we preprocess the data in order to extract the features to support the machine learning classification. So as you can see in this diagram, there are mainly 3 components in data preprocessing step: filtering, sampling, and feature extraction. So in the filtering step, we filter the packets and flows related to the user device in terms of video streaming. And also for the flow level data, we use domain name identification to extract the flows related to the content platform using the keywords such as Google Video, Facebook, and so on. In the sampling step, especially for the packet level data, that means DS packet, we create non-overlapping bins of 0.5 second and put the packets into those bins based on the timestamp. In the feature extraction step, for the packet level data, we create long bins of 5-second sliding window with 1 second step size, considering the 0.5 second bin data that we created in the sampling step. And after that, considering those long bins, we extract features such as total bytes and total number of packets that have been streamed in both direction, downlink and uplink. For the flow level data, which we denote as DS flow and also DSMNO, there can be multiple flows for each trace. So by considering all the flows in a given trace, we extract a couple of features such as average throughput and some bursting features and so on to represent a given trace with the feature vector. So now let's discuss the data classification step in a 360NorVic methodology. For almost all the classifiers that we have in 360NorVic, the base model is XGBoost classification models. And we have put both 360 and normal traffic data mainly into 3 traffic types: YouTube, Facebook, and by combining both YouTube and Facebook data, we create another category called both. And also the unique video IDs that we have for each category, which is 50. We have divided them mainly into train and test dataset, and the traces from the test video IDs are not seen by the classification models at the training phase. There are 2 main scenarios in the classification. One is classification at LAN and enterprise level, and the classification at mobile network operator level, which is a pilot study in our case. So for the classification at LAN and enterprise, there are 2 main categories of classification: offline and near real time. So we apply this offline classification for both DS packet and DS flow data, and we first gather the data and train and test the models offline. And also we try to train these models and test them while changing the amount of data. For the DS packet, we change the video duration, and also for the DS flow, we change the number of flows which are sorted according to the bytes downloaded value in each trace to train and test the classifiers. So when it comes to near real-time case, we apply this model only for the DS packet data, and we take the 5-second long bins as a continuous train to train and test this model. And once the data is arrived, we try to give the classification results as early as possible, and we give these results every 5 seconds after that with the incremental accuracy. So at the classification at mobile network operator level, we apply this classification for the DSMNO dataset, and we first train and develop the models from the data that we gathered using our control experiments, and we aim to deploy these trained models in the wild in our inference phase to see how these 360 and normal video traces are distributed among the users. So now let's discuss the results of 360NorVic in detail. I'll start from the offline classification for the DS packet and DS flow. So for the DS packet at local area network, we could achieve more than 95% accuracy and more than 94% F1 score in the classification for three main traffic types: YouTube, Facebook, and both. And when we increase the video duration, it definitely improves the classification accuracy because the model sees more data during the training phase. And when it comes to the 120 seconds, we see a slight drop in the accuracy because with the too many data, we see that there is a less data in the bins towards the end of the video, making 360 and normal video with more similar characteristics. And when it comes to DS flow data at enterprise level, we could achieve more than 92% accuracy and 91% of F1 score for all three traffic types. And even with one flow, we could see more than 91% accuracy for each category. And we see a slight drop when we increase the number of flows because towards the flows which has low number of bytes downloaded, we see similar properties for both 360 and normal videos. So now let's discuss the performance of near real-time classification of 360NorVic for the DS packet data. So as you can see in this figure, we start giving the accuracy at 10 seconds of the video duration, and after that every 5 seconds we give the classification results with the incremental accuracy up to 60 seconds. After 60 seconds, we see that the accuracy levels off for all three traffic types with a slight decrease. However, we see a more than 96% of max accuracy for all three traffic types. We compare the near real-time classification accuracy with the offline models, and we could see in average 3% improvement in the accuracy for all three traffic types in terms of 360 and normal classification. The reason is in this near real-time case, we aggregate the results every 5 seconds and take the max voting result as the final result, which gave us the higher accuracy than the offline scenario in 360NorVic. So now let's discuss the 360NorVic performance at mobile network operator level, which is a pilot study in our case, where we developed and trained the models using the control experiment data that we collected from operation network. So with the tenfold cross-validation, we could achieve more than 92% of max accuracy for both YouTube and Facebook platforms when we increase the number of flows for the classification. And when we analyze the data downloaded by both platforms, we see that for YouTube, up to third or fourth flows, there is a noticeable amount of data transmitted, and it is reflected in this performance graph as well. As we see, we need at least 4 flows to get the maximum accuracy for the YouTube case. But for the Facebook, we can see having only 1 flow, we can achieve the maximum accuracy level because the majority of the data is streamed using only the first flow for the Facebook case. In 360NorVic, we did a couple of further analysis on top of the 360 and normal video classification. Here I'm going to show you only 2 parts, but for further details you can refer to the paper. For the first part, if I consider this effect of content popularity, we are going to show the what would be the effect if the videos are getting popular by the time on the 360NorVic classification performance. So in this case, for each video ID, we take 70% of the traces for the training purpose and the remaining for the testing. By dividing the traces in that way, we could achieve 0.9 to 1.6 accuracy improvement for both DS packet and DS flow compared to the offline accuracy that I showed earlier. And when we consider this effect of video content, where we analyze the individual video classification accuracy. As you can see in this figure, for all the categories, in average, 40 videos could give the maximum performance. And also there were a couple of videos which were given poor accuracy level, especially for the normal video categories. Those videos had high motion and contrast content. So this effect of video content on the 360NorVic classification, we will keep it as a future work. To conclude my presentation and give you some future directions, in 360NorVic, we have presented a machine learning-based 360 and normal video classification platform, which exceeds packet level accuracy more than 95% and flow level data accuracy for more than 92%. So the importance of this work is we have given the predictions for both offline and near real-time predictions. And also we have shown the feasibility of deploying this model in real mobile network operator level, which can be indeed used to optimize resources of the network and finally improve the quality of experience of video streaming. As the future directions, we aim to conduct a root cause analysis for the performance variations that we have seen so far, and also we will see the impact of viewport aware streaming on the classification performance. Finally, we aim to deploy our train and develop models at mobile network operator level to see how the classification works in the wild. Thank you very much and happy to answer any question.